Hey everybody. I know this format isn't going to be ideal, but I wanted to let you know that I'm working really hard to try to come up with something that will hopefully allow us to end with a somewhat successful semester. Moving forward, what you're going to see when you go into Canvas is I'm going to open up the modules section of the course, and then I'm going to post materials in there by day. So for example, today, once I get this video uploaded to YouTube, you're going to see in the module section for today, 3 things. There'll be a note sheet, so I'm going to try to create these note sheets to align with what we're doing. It'll just hopefully make it a little bit easier for you to follow along with these videos. I'll put a blank copy in there so that if you want to print the blank copy of the note sheet and then work along, while I'm going through the video, then that's an option for you. I will also upload a completed version. So once I'm finished with the completed version, that'll go in, and if you just want to watch the video and then print out the completed notes, you could. If you don't have printing capabilities, then you could take notes the way you would have before. Just watch the video and write down your own notes. Now, the videos are going to stay. You'll have access to those, but you will encounter a few quizzes when you get through, some of the material later in Canvas. You'll have to take a quiz, and if you want to have, quicker access to your notes, is going to be helpful if you have them written. So I'm going to put a completed copy of these notes, a blank copy if you want to print them out, and you'll have the video. All of that stuff will stay in there, and it'll be in there separated by day, and the days will go according to the calendar that I updated on the homepage. So hopefully that will be okay. The homework assignments in Math Lab are still going to be in there and opened up just like they normally would have been. The first due date for homework is April 9th, but it's going to be everything that we do in Chapter 10, so hopefully you're keeping up on these videos. If you wait until the suspension is technically lifted on April 6th to get going, you're going to find yourself pretty behind. Anyway, Chapter 10 that we're jumping to, I know we ended off on Chapter 7 before the midterm there. Is a pretty big jump, but 8 and 9 are not required in our curriculum. They're actually part of 92 curriculum. So Chapter 10 is where we're going to pick up, and it's all about radicals. And so getting started with some basics here, when we're looking at a radical expression, like this one that I have on the screen, the nth root of a is how we would read that. There are 3 portions to it that we should be familiar with, 3 sort of vocab words. So first, we have the radical symbol, right? That's what we call the symbol that is in between the n and the a there. It can be called a radical, or it can be called a root. And we have the number that's underneath the radical or the root, which we call the radicand or radicand. And then the little n there. We don't always see a number there. So, for example, here, we don't see a number like an n, anything written there. That's a square root. So, like when we don't see a 1 in front of an x, we know there's a 1 there. If we don't see a number there, we know it's a 2. But the number can also be anything bigger than 2. Any whole number bigger than 2, so 3, 4, 5, anything like that. Well, that little number is called the index. So the index of the radical is going to be from 2 or greater. So that n can be greater than or equal to positive 2. Okay? So we're just going to make sure we're comfortable with the idea of what it means to take a root of a number. So we're going to look at some perfect roots and evaluating or finding the value of those perfect roots. So when the root of a number has an exact value, like the ones we're going to look at in a minute, we call it a perfect root. And we should be able to evaluate some of these. I'm hoping a few of these we can do without a calculator, but with a calculator is fine as well. So with or without, hopefully many of these we can do without. And I'm going to show you a free online calculator if you don't have one at home. If you do have a calculator, you're probably going to have to use your manual if you have it, or Google, to figure out how to use it for some of these things. But let's see what we can evaluate here. So when we're looking at this first expression, okay, we would read that as the square root of 25. When we're looking for the square root of a number, we're looking for what number are we multiplying by itself to get to that number. So the square root of 25 is 5, because 5 times 5 makes 25, right? Now what if I asked you for the square root of negative 25? Well, the square root of negative 25 doesn't exist, right? If I'm looking for what number could I multiply by itself to get negative 25, if I have to multiply a positive 5 and a positive 5, or a negative 5 and a negative 5, no matter the case, the result is going to be a positive 25. If I multiply two positives or multiply two negatives, that's squaring a number, where whether it's positive or negative, the result has to be a positive. So it won't be possible for us to square root a negative number. So we're going to say that this does not exist. Oops, I can't spell apparently. Does not exist. And in the future, we'll just abbreviate that DNE. Okay? Does not exist. You could also say that it's there's no real number value for it, but we cannot take the square root of negative 25. Okay? There is no real number value for the square root of negative 25. Now, if I move the negative outside of the radical, then that's really a negative 1 times the square root of 25. So this is really a negative times 5, which would make it a negative 5. And then here, negative doesn't make a positive, right? We're multiplying a negative by a square root of something that doesn't exist. So I can't take something that doesn't exist and then multiply by a negative. So this still does not exist. Okay? So negatives under the square root, no good. Now cube roots, I don't think we're as familiar with. I know we've seen some of them before with our sums and differences of cubes, but the cube root of 27, hopefully we know. It's one that comes up quite a bit, is 3, and that's because 3 times 3 times 3, right, gets us 27. When we're looking for the cube root of a number, it's what number are we multiplying by itself 3 times to get to that result, to get to that radicand. So the cube root of 27 is going to be 3. Now, cube root of negative 27. Is there a number we could multiply by itself 3 times to get a negative? Well, yeah, if I multiply a negative 3 and a negative 3 and a negative 3, those 3 negatives make a negative 27. So the result here is going to be a negative 3. Get rid of this, okay? And so we don't have the same restriction with the cube root that we had over here with the square root. So this one, take a negative and multiply it by the cube root of negative 27. So cube root of 27 is 3 times the negative, makes that a negative 3. Here, we take the cube root of negative 27, which we said was negative 3, and then we multiply by the negative, so this becomes a positive 3. Okay, now fourth roots. I know we haven't seen a lot of fourth roots, so maybe we don't know what this one is. Okay, but the fourth root of 81 is asking what number are we multiplying by itself 4 times to get to 81? Well, that's going to be 3 again. The 3 times 3 makes 9, times another 3 makes 27, times another 3 makes 81. Now, what about the fourth root of negative 81? Could I multiply a number by itself 4 times? Could I raise a number to the 4th power and get a negative? No. The answer is here, or what happens here is the same thing that happened with the square root. If I have 4 negatives or 4 positives, the result is going to be a positive. So the fourth root of a negative here is not going to exist, does not exist. Now in the next one, the negative's outside of the radical. That's take the fourth root of 81 to get 3, and then multiply by a negative. So that's doable, it's a negative 3. And then here, I can't take the fourth root of 81 and then multiply something that doesn't exist by a negative. So this still does not exist. Okay? Fifth roots, definitely haven't seen before. Well, in this course anyway. But what number are we multiplying by itself 5 times? What number to the 5th power makes 32? Happens to be 2. 2 times 2 is 4, times another 2 is 8, times another 2 is 16, times another 2, there's 2 to the 5th power there, is going to give us a 32. So the 5th root of 32 is 2. 5th root of negative 32? Well, if I had 5 negative 2's, negative 2, negative 2, that's a positive, that's a negative, that's a positive, that's a negative, right? That result would be a negative 32. So a negative 2 is our result for the 5th root of negative 32. 5th root of 32 is 2, multiplied by a negative makes this a negative 2. And then we have a negative 2 from this result, multiplied by the negative on the outside to make this a positive 2. Okay? So there's some generalizations here that we should hopefully be seeing, hopefully understanding. If we're taking an even root, that means a square root. Even root means the index is even. So this is an even index, like a square root or a fourth root. If we're taking an even root of a positive number, That would be everything we did in blue. Well, not everything we did, but square root of 25 or fourth root of 81. Those are even roots of positive numbers. We got positive results. And then when we try to take even roots of negative numbers, like a square root of negative 25 or a fourth root of negative 81, we got something that does not exist. And that's always going to be true. An even root of a positive number will be positive, and an even root of a negative number will not exist. And then the odd roots, those are the ones we did in red. Odd roots, meaning we have odd index, or indices would be the plural there. If we take an odd root of a positive number, like a cube root of 27 or a fifth root of 32, we're going to get a positive result. And then we saw with the odd roots of negatives that we weren't restricted in the same way that we were restricted with the square roots, that we could take an odd root of a negative and get a negative result. So most of it's pretty intuitive. Okay, even root of a positive is positive, odd root of a positive is positive, odd root of a negative is negative. The only one that doesn't work out is the even root of a negative. An even root of a negative will not exist. Now, all of this can be confirmed with the calculator. Most of your calculators are going to have a cube root or square root button on the home screen, but it might take a little fishing to find the cube root, fourth root, or fifth root. I just want to show you, though, if you have not seen this before, there's a free app. It's the green one, obviously not the messages, but this green box with the parabola going through it here. It's an app called Desmos. It's free. It's on Androids and iPhones. You can also go to desmos.com and access this free calculator. So if you don't have a calculator at home, you can use Desmos, but I want to show you that it can confirm everything that you're doing. Okay? So for example, if you weren't sure, like, what is negative cube root of negative 27, type in your negative. Now my home screen here has a square root, but I don't see a cube root anywhere on the screen. So I'm going to go into functions here. Still don't see any cube roots. So functions and miscellaneous, and now I have this nth root, which gives me the option to put in any index I want. So negative, and then I'm going to make my index a 3, and under I'm going to put in a negative 27, and the calculator confirms for me that that is a positive 3. Or over here, sorry, I'm going to try to move my calculator. If we're looking at something like the fifth root of negative 32 and we're not sure, I'm going to put in, again, go to my functions, I'm going to put in my fifth root of negative 32 because I'm just not sure, and it will tell me that it's negative 2. So these are things that can be evaluated with the calculator. It just might take some playing with your calculator to figure it out. Use Google. It's going to tell you how to do it if you don't already know. And if you don't have a calculator, I would suggest the Desmos app because it's free, okay? So all this can be confirmed with the calculator. The hope was that you wouldn't, how do I get rid of this calculator? That you wouldn't necessarily need it for some of the ones we were looking at, but it's there as an option for you, and obviously you're going to be home working on this. I can't restrict any calculator use, and I wouldn't anyway, okay? So these are some basic perfect roots, and the concept of evaluating them is going to help us with the next concept we're looking at. It will also tie into where we left off in Chapter 7. So we're going to look at radical functions with even roots, okay? Radical function. Remember, an expression doesn't have an equal sign. That's what we looked at a second ago. Putting an equation or an equal sign in there would turn your expression into an equation. And then in your equation, if you had two variables, usually an x and a y, you're trying to establish the relationship for a function. So if we're looking at a radical function with an even root, we're looking at something like y equals the square root of x. So this is a radical function with an even root. Now I chose the square root of x. We're going to call this the parent function. It's the parent even root function. Any radical function with an even root is going to behave like and resemble this function. So I could make it a fourth root of x or a sixth root of x or an eighth root of x. They're all sort of going to behave the same way, okay? Now in Chapter 7, we did just a brief amount of graphing. We said if we were going to make a graph, we need some points to connect. So we can make a table of values where we plug in some x's and see what happens back for y. Now when we made our tables before, we picked, like -1, 0, and +1. And then we saw what happened and tried to connect the dots. But it's going to be an issue here because -1 under a square root isn't possible. So it's not going to be possible to put anything negative underneath our square root. In fact, the smallest number we can square root is 0. So I'm going to start this table of values at 0, which means this graph is going to start at 0. So when I plug a 0 in, the square root of 0 is 0, so that's our output. And I'm going to go ahead and put a 1 in, because the square root of 1 is 1. And now I could put a 2 in, but since it's a decimal, the square root of 2 would be a decimal. I'm not going to deal with graphing a decimal. The same thing with 3. So I'm going to jump to positive 4 here, because that's another perfect root. What's the square root of 4? It's going to give us a 2. And then 5, 6, 7, 8, 9, not perfect roots. I mean 8, not perfect roots, but 9 is. I can take the square root of 9 and make 3. So I'm going to put a 3 here. So now I have a few points on my graph that I can plot. So I got a point at 0, 0. I got a point at 1, 1. And then the square root of 4 was 2. And the square root of 9 was 3. Now when we go to connect these, I could keep picking larger values of x, and what will happen is the value of y will slowly start to grow. So in this direction, the graph is going to continue. But this endpoint here is at the origin is going to stay an endpoint. There isn't anything smaller that I can take the square root of, so there won't be any graph that happens to the left of that point. So this is what the square root function looks like. And this is what any even-rooted function will look like. If you put in a 4th root of x or a 6th root of x, the same behavior is going to happen. The steepness might change a little, but it's going to sort of make this little hill-shaped graph where you have an end point or a starting point and a graph that will go forever in one direction. Now, it's possible that it could flip around and go the other direction, or shift up or down or left or right, but this is the shape you're going to see on any even-rooted function, on the graph of any even-rooted function, okay? So which means, it will connect to what we were doing in Chapter 7 of finding the domain. All radical functions with even roots have restricted domains. Okay, there's certain numbers we cannot take the square root of, or 4th root of, or 6th root of, or even root of, right? We can't take those even roots of negatives, so we're going to have graphs and functions that are restricted in terms of what x's can be plugged in. So each of these graphs or each of these functions would have some starting point, as we saw, and then they continue infinitely in only one direction. Okay? Now, if you're looking at an odd root function, an odd root function doesn't have the same problems, and we saw this a few minutes ago. We can take cube roots or 5th roots of positives or negatives. So just so you can see the concept on a graph, let's look at the cube root of x. Again, the cube root of x, 5th root of x, 7th root of x, all these odd root functions, they're going to behave similarly and resemble one another. So the cube root of x is our parent odd root function. Now when we go to make this table, I can take the cube root of 0 and anything positive or negative, but I want perfect roots in here. So I can take the cube root of 1 or negative 1. I can also take the cube root of 8 and negative 8. So the cube root of negative 8, what number are we multiplying? What number are we cubing to get negative 8? Would be negative 2. Okay, how about the cube root of negative 1? Cube root of negative 1 is going to be negative 1. Again, you can confirm that with your calculator. Cube root of 0 is going to be 0. Cube root of positive 1 is going to be positive 1. And cube root of positive 8 is going to be positive 2. Okay? So in this graph, we've got a point at negative 8, negative 2, negative 1, 0, 0, 1, 1, and 8, 2. And I could keep picking x's in both directions and keep getting outputs in both directions. So if you notice on the right side of the graph here, we have a graph that looks pretty similar to the square root of x, which makes sense. This is a radical function. So this side of it looks the same, where the cube roots of positives are positive, just like the square roots of positives were positive. But now because we're not restricted, because the cube roots of negative are negative, we have this other side of the graph happening as well. So we have like the mirror image, right? Not only are cube roots of positives positives, but cube roots of negatives are negative. Okay? So all of our odd root functions are unrestricted, and unrestricted, okay, that means they have unrestricted domains, right? We see this graph go left and right forever because we can plug whatever we want in for x. So our domain here it's unrestricted. That means it's infinite, all right? So you might be asked to find the domain of a radical function without doing any graphing. And you're going to use the concepts we just talked about. So if we're dealing with an even root, then the radicand, that is the part under the radical, it has to be 0 or anything bigger, okay? At least 0. So what we do is we make the radicand greater than or equal to 0. That's how we say at least 0 mathematically. And we solve that inequality to figure out our domain. Now, if it's an odd root, there are no restrictions. So if it's an odd root, just recognizing an index of 3 or 5 or something odd means your domain can be all real numbers, remember that symbol, or anything from negative infinity to positive infinity. Okay? So y equals the square root of x plus 4. That plus 4 has an effect on the graph. Whether we know it or not doesn't matter. I know that if it's a square root, then the radicand, the part under the square root, has to be at least 0. So if I make it greater than or equal to 0, I have an inequality that I can solve to find that domain. And we solve this just like an equation. If I subtract 4 from both sides, then I can see that my x values that I plug in, they have to be greater than or equal to a negative 4. Which makes sense. Think about it. If you plug negative 4 in, negative 4 and 4 makes 0, and you could square root 0, then anything else that's bigger is going to be fine. So if you plug in negative 3 plus 4 is 1, and I can square root 1, and so on. So I could say this domain is all x's such that these x's have to be greater than or equal to negative 4. That would be the set notation. Or if you wanted to write the interval, think about your number line graph. Right? If you could be negative 4 or anything bigger, then your interval would go from negative 4 to positive infinity. So we could also say everything from negative 4 to positive infinity. And we can include that negative 4. We can square root the value we get when we plug negative 4 in. Okay? So either one of these would be acceptable. The set or the interval would be fine. Okay? So then here, same concept. We have a fourth root. So a fourth root behaves just like a square root. Our radicand, in this case 2 minus x, has to be at least 0. So if we subtract 2 from both sides, minus 2, then I see that a negative x has to be greater than or equal to a negative 2. Now the next step, we're dividing both sides by the negative 1 that's here. So that's going to give us x, and then I don't know if you remember the rule for solving an inequality, but if you divide or multiply both sides by negative, this symbol has to flip, and then negative 2 divided by negative 1 makes a positive 2 on this side. Let me go back to blue. Positive 2 on this side, okay? So a little minor detail when you're solving an inequality, right? If you multiply or divide by a negative when you solve an inequality, then you're going to have to flip the symbol. Flip the inequality symbol. So we started out with a greater than symbol. It flips and becomes a less than symbol. Okay? And later, when we learn a little bit more about graphing and what we call transformations, that will make a little bit more sense. But for now, you can also think about what this is saying here. When it says a negative x is greater than or equal to a negative 2, that negative we can think about as the word opposite, right? Well, what's the opposite of being greater than or equal to a negative 2? The opposite would be less than or equal to a positive 2. So the opposite, the negative or the opposite applies to both the symbol and to the negative 2. Okay, if that helps clarify that for you. All right, so we could say that this domain is all x's such that these x's have to be less than or equal to positive 2, or think about your number line graph, right? You can be 2 or anything less, then that interval would be everything from negative infinity up to positive 2. So either one of those we could use for our domain here. Okay? Now, looking at number 3, we've got a ideal scenario here. Give me 1 second. I'm going to move this a little bit. There we go. Okay, looking at number 3. It's a cube root, and a cube root is not restricted. So as soon as we see that we have a cube root there, we don't have to do any work. If it's a cube root, I can cube root positives or negatives and get results, which means it's unrestricted. As soon as I see that this is a cube root, because that is an odd or a cube root, this domain is unrestricted. It's everything from negative infinity to positive infinity, or all real numbers. Okay, and the same thing here. As soon as you recognize you have an odd root, right, if that's an odd root, an odd index, then this is an unrestricted function. I can plug whatever I want in there for x and take the cube root or fifth root or odd root of whatever I have left. So everything from negative infinity to positive infinity, or all real numbers, are going to be good to go. Good to be plugged in there. Okay? All right, moving right along. So we've got the ability to evaluate perfect roots, which you can confirm with calculator. The ability to possibly graph a radical function, which you won't be doing a lot of that. That's more for understanding the domain piece, which you just looked at. And then somewhere in 10.2, we start looking at what we call rational exponents. Now, if you remember what it means to be rational, in Chapter 6 we did a whole function of rational things. Rational expressions and equations were all those with fractions of polynomials. If we're looking at a rational exponent, that means we have an exponent that is a fraction. And there is definitely a connection between rational exponents and radicals. There's an equivalent way to take a radical and write it with the rational exponent, and vice versa. So here's what we know. If we have the nth root of a to the mth power, so some radical expression where the radicand has an exponent and the radical obviously has an index, that's going to be equivalent to. Equivalent means it will look different, but it will have the same value. So it's equivalent to a to the mnth power. So that is written with a rational exponent. And you can see if you're going from the radical form to the rational exponential form, all we're doing is dividing the exponent by the index, taking the m and dividing by the end. So we should be able to convert from radical form to that rational exponential form. And we're going to do it by dividing the exponent by the index. So here, when we see the fourth root of x to the fifth, that is equivalent to x to the 5/4. Has the same value, just looks different, right? Or here, we can say this is equivalent to x to the 6/3. And because that reduces, we can go further and say that's the same as x squared, right? Or here, this is, remember, your index that's invisible there is a 2, and equals 2. So this is the same thing as x to the 3/2 power. Or here, we got an exponent of 1 when we don't see it. So we have a coefficient of 4, which stays a coefficient of 4, and then it's x to the 1 gets divided by 5x to the 1/5 power. Now here you have to be really careful on number 5. If we tried to do this, 9x to the 4/7, then 9 is a coefficient, but we really need 9 to be part of that 7th root. So it's not going to be equivalent here because the 4/7 power is only applying to the x and nothing is applying to the 9. So what we want to do here is remember, as when we talked about our exponent rules, that everything has an exponent. So that 9 has an exponent of 1, which means when I go to rewrite this, it's 9 to the 1/7 and x to the 4/7. So each of those exponents gets divided by 7. Okay, now if you were visualizing this differently, if you wanted to think about this as 9x to the 4th all as a single thing, you could have also said that this is 9x to the 4th all to the 1/7. So either one of those is equivalent. If you don't like that second one, don't worry about it. I think this form is perfectly acceptable. It's just wanted to show you the option there in case your brain was functioning that way. All right, feel free to pause and try this one out. Otherwise, I'm going to keep rolling here. So this is 5x, that whole quantity is squared and under the cube root, so the whole quantity gets the 2/3 power. Okay? Either one would be fine there. All right, so if we can go from our radical form to rational exponential form by dividing the exponent by the index, here we want to go in reverse. So we have to remember, if we're going to start with the rational exponent, is that the denominator is our index. Okay, the bottom of the fraction is the index, and the numerator is the exponent. So when we're looking at x to the 1/2 power, we want to read it from the bottom of the fraction and then sort of up this way. So I always read this in a circle. So I'm reading the bottom of the fraction first as the square root of x to the 1st power. So if I read this, again, x to the 1/2 is equivalent to, that means it looks different but has the same value as the square root of x to the 1st. Now I wrote the 2 and the 1 just so you could see them, but we don't really write an index of 2 and we don't need an exponent of 1. Okay, similarly here, this is a square root of x to the 9th. So the square root of x to the 9th. Okay, here is the 10th root of x to the 3rd. So the 10th root of x to the 3rd. And when you're writing these, make sure that your index is written a little smaller and sort of tucked into the curve of the radical there. You don't want to write like this, because then it looks like 10 times that radical, okay? So make sure when you're writing your index that it's written kind of smaller and tucked in there. All right, here, be careful. Your 2/3 power applies only to x, not to the 2. So the 2 that is a coefficient has to stay a coefficient. And then it's the cube root of x squared. So the cube root of x squared. Okay, here the 2 and the x both get the 2/3 power. So the cube root of the whole thing squared, right? The cube root of the whole thing squared. And then lastly, again, if you wanted to pause and try it, got to be careful here. The 3/4 power doesn't apply to the coefficient of -1. It only applies to the x. So the negative coefficient is going to stay a negative coefficient. And then it's the 4th root of x cubed. So 4th root of x cubed. Okay? And the purpose, or part of the reason that we want to be able to go back and forth here is so that we can evaluate these expressions that look a little strange. For example, evaluating something like 125 to the 2/3 power. Okay, I don't know if you've done that before, but it looks intimidating. So what we want to do is rewrite it in radical form because it's going to look a little more manageable for us. And then we're going to try to evaluate that way. But the good news is these expressions that don't contain any variables can all be verified with the calculator. And then you'll have to play with your own calculator a little bit, but I will show you how to verify these with the Desmos one that I showed you. So by all means, verify what you're doing with the calculator. All right, so 125 to the 2/3 power is the same thing as a cube root of 125 squared. So this is a cube root of 125 squared. Now we have the option here of taking the cube root of 125 and then squaring, or of squaring the 125 and then taking the cube root, but it makes a lot more sense to take the root first to make a smaller number to square. So we're going to take the cube root of 125, which is 5, and then we're going to square that to make our final result 25. Okay, here we've got a negative coefficient, and then we have a square root of 121 cubed. A square root of 121 cubed. And I'm going to leave the negative, the square root of 121 first, which would make 11, and then cube the 11, which makes this a negative in front of 1,331. I'm sure you didn't know, but I have lots of useless information in my head. Okay? Now this one, we've got a negative exponent. Now if you remember the negative exponent rule, it says anything with a negative exponent belongs on the other side of the fraction. So really we're looking at, instead of 16 to the negative 1/4 on the top of that fraction, right? It's on the top of the fraction right now. It needs to be 16 to the positive 1/4 on the bottom. Now this becomes 1 over the 4th root of 16 to the 1st. So the 4th root of 16, and what are we multiplying by itself 4 times? What are we raising to the 4th power to get 16? Happens to be 2. So our answer here is 1/2. Okay, and if these are tricky for you, don't sweat it. Remember, you're going to be able to confirm with the calculator. And I'm going kind of fast, but let's try this guy. So this is the 5th root of 32 cubed. 5th root of 32 cubed. 5th root of 32, we had that at the beginning of the notes. 5th root of 32 is 2. If you take the 2 and cube it, then the result is 8. So 32 to the 3/5 power is just 8. Okay, fancy way to write 8. The 1/2 power is one that actually occurs a lot, and that's one we got to be pretty familiar with. This is really just a square root of this thing to the 1st. So So when you're looking at a 1/2 power, knowing that that's just a square root is going to be helpful for you the farther you go in your math career. So we've got a negative coefficient, and then we have a square root of 25 over 121 to the first, which is just 25 over 121. So a negative square root of 25 is 5, and square root of 121 is 11. All right, and then lastly, we've got a negative coefficient, and then a cube root of 27 squared. Cube root of 27 squared. So we did the cube root of 27 again in the front of the notes, beginning of the notes. So cube root of 27 was 3. This would be a negative 3 squared, and 3 squared is 9. So this is a negative 9 for that final result. Okay, now again, all of this can be confirmed with the calculator. And if you're going to use your calculator to confirm or to verify, then do it from the initial step. So let me show you what I'm trying to say here. Some of this. If I wanted to verify that 125 to the 2/3 is really 25, I don't want to put the cube root of 125 squared in the calculator because it's possible that I made a mistake just in the rewriting. So I would be putting in 125, and I want to raise it to the 2/3 power. So I have this AB button that will give me an exponent. Your calculator might have a caret button to make an exponent, but in that exponent I need 2/3. So I need the whole fraction to be in the exponent. Okay? And then it confirms that my answer there should be a 25. Now I think for some of your calculators, if you wanted to type in 125 to the 2/3, you're going to type in something like 125 and then a little caret button to give you a power. And then you need to make sure that your power depends on how your calculator writes. You need to make sure that the 2/3 is all in the exponent, so you may have to put the exponent in parentheses. But what I would do is take some time to play around with your calculators. The answers I gave you here are obviously going to be correct. So take some time with your calculators to make sure you can input the original problem and get to the final answer that I gave you there. And if you're struggling with your calculator, try to use Google to help. And if your calculator just stinks, then maybe download the free app, because you saw in the app here that plugging in 125 to the 2/3 power was pretty simple for me. Okay? Or even something like this. I'm going to look at number 15. I've got a negative, and then a parenthesis, and then a 25 to make the fraction just hit divide, and then 121. And then I'm going to close the parenthesis, and then I'm going to use this AB button to give me an exponent, and the exponent needs to be a 1/2. And it gives me negative 0.45 repeating. Now, it doesn't look as the same as the answer I have here, but if you'll notice in blue, next to where you typed in the fraction, it looks like a picture of a fraction. If I tapped that button in the blue column over here, it will go back and forth from a decimal form to a fraction form. And so now I can see that negative 5/11 is the same answer we got. Okay, so get comfortable with your technology. Do your best, right? Use Google to help you where you can. And if your calculator again stinks, maybe try downloading that app. But anything that doesn't have a variable in it can be verified with your calculator. Okay, so the homework is set up in the math lab for you, and the next video will come out on Thursday. And as I mentioned before, they'll be day by day. All right, so I know this format isn't ideal, but I'm trying my best, and I'm here for you. So if you want to email me with any of your questions, I would be more than happy to try to help you work through whatever your issues are. Okay, so I look forward to hearing from you.